Okay, before I get to talking about Oersted's experiment, can I skip this slide and can I go to the next one real quick? I want to talk a bit about current, just to make sure that we know what current is. Okay. Historically, Ben Franklin had to choose something to be positive, something to be negative. And he thought that the stuff that like moved and transferred through conduction, he thought it was positive stuff. And we still use that to this day. We call it conventional current. The problem is it's not actually the positives that move. Okay. Technically, it is the electrons that move. And so have I already discussed with you guys the idea of electron flow versus conventional current? It is a pain in the butt. And we're going to discover this a lot today. Sometimes we're going to talk about current, which means we're pretending that positive things are moving. But we know they don't. And sometimes we're going to talk about electron flow, which is the actual direction that electrons flow. Does that make sense? So, sorry this sucks. It's why engineers hate this sort of thing. Okay. Here's my slide on current then. Current is about how many electrons move. Okay. If I were to give you an analogy of current versus voltage again, imagine I wanted you guys to walk down the hallway from here to the office. If you guys walked one at a time, we would have low current. If you guys all walked at once, we would have high current because more of you are moving. Does that make sense? If you walked, you would have low voltage. If you ran, you would have high voltage because voltage has to do with your energy. Fair enough? So this is a formula I need you guys to know. It's on your data booklet. If you want to figure out how much current you have, it's how much charge you have per time. The more charge you have moving per unit of time, the more current you have. And we measure it in amps. And for whatever reason, its symbol is I. I don't know why. We ran out of letters. Fair enough? Okay. And then the second slide here just talks about what I've already mentioned before. Electrical current, if I talk about electron flow, that's what actually moves. Electrical current always goes from the negative pole to the positive pole. That is the way that electrical current goes, from negative to positive. That's what electrons do. Any of you guys in Chem 30 currently? You guys doing redox and cells yet? Okay, so you're going to come across this. This would be like your anode to your cathode, if you guys get to that in like your battery type stuff. Electrons go anode to cathode. However, conventional current, based on Ben Franklin's horrible mistake, actually goes from positive to negative. And so if you ever describe conventional current, it goes the other way, which is like annoying. Okay. So many of my slides, I have a ton of pictures that are going to come on like these feature slides. Many of these pictures are going to be like backwards or forwards, depending on whether it's like conventional or electron flow. Okay, let's go back to our first slide then. So this experiment Oersted discovered. He discovered that basically we could make electricity create magnetism, hence like the electromagnetic force. And the word I want you guys to use is induced. He induced a magnetic field, and it was always perpendicular to the direction it was going. The compass was parallel, and he got it to deflect to a 90-degree angle. Does that make sense, that picture that I kind of drew right here? It was, the electrons were going this way, the compass was going this way, and he got the compass to rotate. Magic trick, right? So, anyways, let's talk some more about that starting here. This sucks. I'm so sorry. This is not the most easy way of learning things. What we have are what's known as our 3 right-hand and left-hand rules. Your left-hand rule is if you ever are working with electrons moving. And your right-hand rule is if you ever work with conventional current. So you're always flipping back and forth between using a hand. And the idea is your hand is a manipulative to help you figure out things like force and field and magnetism, so you can kind of keep track of things, okay? Unless you have a good reason to think otherwise, assume it's going to be electrons, which means you're probably using a left hand for all of these scenarios. Okay, so this is very like 3-dimensional spatial kind of concept. Okay. One more convention I need you guys to know. Because we're talking about things in 3 dimensions, there's the up and down dimension, which would be like this. There's the side to side dimension, but we also have to be able to go in and out of the page. So if you ever see a dot, that implies that something is going towards you. If you see this dot, this is like the tip of an arrow coming out of the screen towards you. No, X. So X is flowing in. So the analogy I give here is imagine there's like the back of an arrow. That's going away from you. So if you ever see this, it's like, I mean, imagine you have like 3D glasses on and you're at the theater. This is something that would be coming out of the page, and the X is going into the page. Because we need to have the X, Y, and Z dimensions now. Unlike in momentum where we only do things in X and Y, we have to go three ways. Does that make sense? This is the reason why these hand rules were developed, because it kind of gives you like some spatial three-dimensional, I don't know, does that help at all? So let's try the first one. This is what Oersted discovered. This is going to be a left-hand rule. If you guys can kind of picture and use your own hand, this is a person's left hand right here. Okay. And the reason why we're using the left hand is because electrons are flowing up in the wire. Okay. So what we're saying is that electrons are going up this wire. Okay. What we've discovered is that in circles around the wire, a magnetic field is being formed. And so it really depends on where you are in 3 dimensions as to which way a compass would point. Let me give you some examples. Let's say that the compass was over here. Okay. The compass needle would be pointing like towards us. But let's say you put a compass like in front of the wire. Then the compass would point that way. And if you put a compass over here, it would point like into the screen. And if you put the compass needle behind the wire, it would point that way. And so what we've discovered is that we can actually cause this thing to deflect any direction we want, depending on where, like in the circle, you happen to be. Okay. And what Oersted kind of discovered in his experiment is he set it up so that it was supposed to be side by side. And as soon as he flipped on the wire, north was supposed to be going this way, for example. And as soon as he turned it on, the needle deflected so that it turned that way. That's how we got it to like maneuver a little bit. Okay. So this is known as our first right-hand rule. If you ever have just a single wire that electrons are running through it, you can actually deflect a compass. Okay. Now, this is a picture I have, though, for a right hand. You might notice that if you took your hands and tried to compare them, this is now someone's right hand here. And so this would mean that this is not electron flow. This would now be conventional current, which is what would happen if positives were moving. We know positives don't actually move, but this would be how you'd use your right hand instead if somehow that was the case. So 9 times out of 10, you're probably getting electron flow. But in the real world, we use a conventional current way too much, and it's a pain in the butt. Okay. So let's try an example here. Here's a wire. I want to put a compass right here. Here's where we're going to put a compass. Which way is the compass going to point? So let's talk this through. This X, what does that mean the wire is doing? Going into the page. So you guys may need to watch to look at me here, but like I'm going to take my left hand and I'm going to point my thumb towards the board. Okay. Now consider your fingers after that. My fingers are going kind of in a clockwise direction, if that makes sense. So if I were to draw a field around this, it's going to go like this, and this, and this, and this. Which way would the compass be pointing? Up. The compass here would point up. Can you guys kind of figure that out? And I may need to like try this with you like in smaller groups, because it doesn't work fantastic like in a big group. But yeah, point your finger into the page with your left hand. Your fingers are going in a clockwise direction. So a compass in this location here would point up. Which is weird because compasses don't normally point up. They would point like towards a pole, but we could actually move it that way. What if you put a compass over here? Yeah. What was that? Oh, did I say the wrong one? Oh, you're right. Yeah, sorry, that is counterclockwise. Sorry, my bad. Minus the fact that I used the wrong word, did you guys get the concept, though, as to which way the compass would point? You're right, though. That is counterclockwise. Thank you. Okay. You're going to get theory questions like this where they're going to give you a picture, and they're going to say, like, which way would the compass point? Right? So this one's a pretty basic one, but we'll try some other ones later. Okay. Here's the second rule. This is what I showed you guys with my wire right there. And I'm going to pause for a second here, and I'm actually going to ask you guys to come to the station here and see the manipulative, how it works. This is called a solenoid. Anytime you have like wire wrapped around in a circle, This is the name we give it. It's called a solenoid. Okay. And often in the solenoid, we put a piece of metal, like through the middle of it, like a core. Because then what ends up happening is the magnetic field lines line up through the middle. Okay. Here's the basic idea. If you were to wrap your fingers around the core in the direction that the wire is wrapped, see how the wire is coming from here? That's kind of like the back part. I'll use a different color actually. See how the wire is kind of coming around the front? That's kind of like the back part of your knuckles going this way, right? And then see how your fingers are wrapping around the back side of it? That's how this is always being wrapped around the back side. Okay. If you use your left hand, your thumb is the direction of the magnetic field, meaning that this side right here will be the north side of the magnet, and this side will be the south side. Now we should be able to make a prediction as to which side is north and south. And that's really abstract to look at. So come with me to the front here, and you guys may actually need to come a little closer to see this. So feel free to get out of your desks. But let's actually look at the wire that I have wrapped here. Okay. Okay, so here's my wire. If you guys can see, the wire that's like extended, there's one that's on this side here that comes out, and there's one that's on this side right here. Okay, I need to make sure that I wrap my fingers in the right orientation. And so to do that, I'm going to try to like set it up properly. I think I need to do it like this. Can you guys see how my pinky finger is kind of matching up with this wire as it kind of goes over it like that? And how like, if you can kind of see this here, how this is kind of like running up my finger as it starts wrapping around. This is the direction, me grabbing it like this, that like I'm matching my hand up properly. I like my pinky finger is probably the best indicator. My pinky finger is this last wire going like that. Does that make sense? Based on this orientation, okay, if the electrons do go around like this, that should make this guy the north pole because that's where my thumb is. I just have to make sure that I set the electrons up properly. Okay, so you know how I have two different ways that I can hook these up? I could either go black here and red here, or I can flip it around. Okay. If I want electron flow, electrons go from the negative to the positive. So I'm going to set up the negatives starting here to the positives ending here. So the electrons are now going, did I do that right? No, that's backwards. Why is that backwards? Because the electrons are going here. I need it to be the other way around. Let me do that again. I need the electrons to start here, go through all these wraps, and to start here, go through all the wraps, and finish with my pinky finger right there. Well, my thumb tells me which way north is then. Okay. So like if you can agree, ignore my thumb for right now. This takes a while to get used to, by the way. Bear with me. Okay, this is not something you'll get like the first time. The electrons are going over the top in this direction here. And the reason I can tell that is because it's finishing with my pinky finger like that. And so the electrons seem to be starting from this black pole right here. They're going wrapped in this orientation here and finishing here. Based on that logic, since my thumb points this way, I should now have a north pole. Let's test it. Shoot, that didn't work because we said that was south, right? Why didn't that work? I do got to check the way it's wrapped here. Is that, am I doing this backwards? Okay. Yeah. So maybe I need to go, like this here. This is where they're starting, and this is where they're finishing. Yeah, okay. Let me do that again here. Maybe if I hold it differently here. Here's where we're starting, and here is where it's wrapping. And what should hopefully occur here, okay, so I'm starting with the electrons at the negative. Okay, let's see. So it's starting here. Now, which way is it going here? The electrons are going, no, that's not the right way then. It should be the other way. I should do it this way. This is tricky, by the way. Like, this is not the easiest thing in the world to figure out. It is a pain in the butt every single time. Yeah. It should, because the electrons should be coming out of the negative, going through this thing and going to the positive. That's what we're hoping for. So I just got to get the orientation right here. I've got this guy looped, though. I want to change the looping just to make sure that I'm not missing it that way. Okay, I'll just take a few wraps out here. Okay, we're gonna make this work. So I'm using my left hand. Okay. I want the electrons to go out of the negative here. So I want to start with the electrons here. So maybe I'll hold it like this. No, not like that. We'll hold it like this. Okay, here's how I'm gonna hold it. The electrons are gonna start on this part here. No, that's still not it. Yeah, that makes sense, right? Where it starts would be the south. I just always struggle with how to orientate it here. Going from here. Yeah. Okay, let's try this now. I think maybe I have the orientation right. Because we want the electrons to go towards that side, right? So the electrons are starting here, right? And finishing here. Is that what I did wrong? Okay. You can see why engineers really hate conventional versus electron flow, because this sucks enough as it is. I'm struggling with this. Okay, so hopefully now this is the North Pole. I hope this works now. There we go. Yeah, see that now? Okay, so I got the North Pole to go there. Whereas if I flipped the orientation of these wires, which is what I had before, then what I really need to do is I need to switch my grip around, go this way, and now the North Pole's on the other side. Okay. You guys are going to get a chance to try this because I've been doing this for a while and I still struggle with it. It still takes some experimenting. We're doing this on Monday, so you guys get a chance to try to figure this out. Okay. So if it clicks already, that's great. If it's not clicking already, don't stress over it. We need to try it. Yeah, that's probably a good way of thinking of it, right? So I just need to make sure I set them up properly. So anyways, let's go back to this one here. Let's try some more examples on paper, and we'll try some more in real life when we get a chance to. It does seem like a few of you guys are getting it because you found my mistake already. So let's try an example here. Okay, so let's try this one here. If the electrons are wrapping around this way, like going down, coming up the other side and wrapping around. If you can kind of set up your hand, maybe I should go to the front even. I'm using my left hand, okay? My fingers are pointing this way, and the reason why, it's really hard to get this, but can you guys see how my fingers are wrapping underneath the bottom like this? When I put my hand in this really awkward scenario? These electrons are going through the bottom like that, which is why the North Pole goes this way. Okay. If my hand was going this way, the electrons would be going over the top. But it's not wrapped under, over, it's going over, under. Do you guys get what I'm saying there? If you had a string of some kind, I have two ways I could wrap this. Here's the object. I could start here and go this way, or I could go that way. Right? There's two ways you could wrap this thing. So you got to figure out which way the wrap happens to go. And that's the single hardest part. So here, I'm looking at the bottom. See how it's going underneath the bottom like that? That means that my hand should be like this. And I'm starting here, and the wrap is going underneath, hence my hand's pointing this way for north. And it's awkward sometimes to do. Where's my board? Here it is. Here's another one. Okay. Let's see if we can figure this one out here. The electrons are going from the positive pole. Sure, yeah. No, this was electron flow. Yeah. Yeah. Okay. So let's try this one here. Again, I'm going to try to go electron flow as much as I can. Here is the positive pole of a battery. Here is the negative pole of the battery. And I don't love the way they've done this because this actually kind of implies that things are going from positive to negative. And things don't actually go from positive to negative. So therefore, on this one here, I'm going to use my right hand. And you're probably going to see this one better. As you hold your right hand up, can you see how my fingers are curling over the top like this? And therefore, my thumb is pointing to the north, right? I'm starting here, and I'm saying my hand is wrapping over the top. That's the way we wrapped it. I could have wrapped underneath, but this was a over sort of wrap around. And so that's why I'm using my right hand on this one, though, because they indicated that the electrons were going from positive to negative, which is actually conventional current, not electron flow. Okay. We're going to need practice on this, okay? I can talk to you like this for an hour, and I don't think it makes it any better. So we will try it. Yeah. You could, yeah. So then what we'd have to do if we used our left hand is we just have to know the electrons are actually going this way, which means I'd be wrapping my hand like this, I guess, right? Or maybe like this, where it went around in the under orientation, and we did this, no, this way. It would be my left hand, because it still has to point north. And here it is going over and over and over, if you can kind of picture that. Okay. This is tough. Well, I wrote a note on here, actually. I said here, you can always tell when someone is doing this on the diploma exam, because they'll be like trying to orientate their hands all sorts of weird ways on the diploma to figure this out. Okay, here's another one. Let's just kind of see if they make sense to you. Here's a battery. Okay. Can you guys see how this is like the over wrap here? It started by going over the edge of the coil, right? So manipulative again. Here's my wire, right? Here's my nail, and over here it started by going over the top before wrapping around like this. That's the orientation that we chose to wrap it, like this. Does that make sense? Okay. So this is the positive end of a battery, this is the negative end of a battery. Let's use our left hand. Okay. Which way do electrons go? Electrons go from negative to positive. So I need the electrons to go this way, which means if I wrap my hand like this, do you see how, like, if I had an object, and I wrap around, here's my finger wrapping around the back, and then my finger is that one right there, which is why my hand points that way. Yeah. Great question. Okay. 9 times out of 10, it's probably going to be electron flow. Okay. So if it doesn't say otherwise, go electron flow. But I do have some old diploma questions they used to ask back in the day where they would say conventional current. The truth is that this is what drives engineers nuts. Because if you're an electrical engineer, you have to know which one is which. And in real life, we label things according to conventional current. And yet we know that that's actually not the way that the electrons actually flow. And so when I was working with the battery right here, I know that the electrons are going from negative to positive. But some people say that current goes from positive to negative, which is like, this is stupid. So yeah, it's frustrating. Let's try one last one here. Okay, you can see that this person right here is actually using their right hand, okay, which would indicate that, like, if they're putting their right hand this way, the only thing I think I wanted to get out of this one is that this must be talking about conventional current then, right? Because if they're using their right hand, then what's actually happening here is, let's see, there I have this right. There's my right hand. The electrons are going from here. Is that their right hand? That's their right hand. Field's going north there. So then, yeah, so this is backwards though, right? Because normally you would want to think that the electron should go the other way, but this is conventional current, which is why it feels like it's reversed. Because you probably would want to use this hand instead, but it's the other way around. That's your second rule. Okay. Now's as good a time as any to point this out here. I wrote a John Dewey quote on the board because I think it's appropriate for you guys today. It's to give the people something to do, not something to learn. I can talk to you about this, and you're probably going to understand it like this much here. You're going to understand it way more once we actually start doing something with it. So please don't freak out if, like, my explanation is not good, because I don't think anyone's explanation for this topic is good. It's like, it's weird. Okay, here's our last one. I'll stay at the front here, I guess, because I need to do a lot of diagrams. It is actually possible to get a wire to move inside a horseshoe magnet. I wish I had some wire. I'd demo it for you. We're going to do this on Monday. I don't have enough wire, though. That's the problem. Well, I don't want to unwind it. Well, let's try it. Here. I don't want to waste. I want to keep it, though. Here, let's try this. I don't know that we're going to see it right now, though, but we can try. Okay, I'm going to hook up the current here, and Malik, I'm going to need your help. You have to hold it for me. We're not going to get electrocuted. It's very little current. But I need you to hold that, basically. Okay, I don't know how well we're going to see this, but what I'm going to do is I'm going to try to hold this here. I need one more set of hands. Can someone come and flip on the current here? What we're hopefully going to see is that this wire is going to move, not because Malik and I are shaking, but because the actual current should move. Can you just turn on the electricity? Yeah, we're not going to notice it. I need to set this up a little bit better. What we should see, though, is that this wire here is either going to move like in or out. and vibrate just like you see it there. The problem is that like we're not holding it straight enough, and this magnet's not strong enough. I will. Can I do this on Monday though? Because I actually was planning on doing this during a lab experiment. So here's the idea though. Imagine that you have a magnet and you have a wire through it. We can actually get this wire to move up or down depending on how we orientate it. And so this is our third rule. It's about a charge in the field and how it deflects. Okay. Here's the best picture I've got. If we're talking about electrons, which are negative, use your left hand. But if you're ever talking about an alpha particle or a proton, use your right hand. Okay? But most of the time, it's electrons that are moving. Here's the way it works. Point your hand towards the south pole. The reason why you're pointing your hand towards the south pole is that that is what a north end of a magnet would do, right? A magnetic field is what a magnet would do. A magnetic field is what a compass would do, and it points towards south. So I'm going to point towards south. Your thumb is the direction that a particle is moving. So an electron is moving this way. What's going to happen is your palm is the direction that it's going to get moved to. So this electron right here would actually get forced into the page, or like kind of downwards. And that's what this picture is right here. Again, this makes way more sense when I set it up with a lab. Here's a picture using someone's right hand. Okay. But let's try an example here. Okay. Let's say that we have a negative electron, and the electron's going this way. Here's how you set up your hand. Use your left hand, point towards with your fingers towards the south pole. Okay. Then it was going this way here. Can you guys see how the electron, it's been drawn so that it's going to like deflect downwards? But the positive proton, this is where it gets awkward. You'd point your hands towards the south pole again. Your thumb is the direction the proton's moving, and it would actually deflect upwards. Be patient, okay? You don't have to get it today. Let's try the math now. You guys are going to like the math, okay? That's going to make way more sense than these hand rules. And I will try to give you guys, through activities and assignments and practice questions, a chance to try it. Because like it's entirely like abstract and hypothetical. It's really, really, really hard for me to like explain it well. Okay, so don't stress if you don't get this. Let's move to the math. You guys will like the math part better. There are two formulas we need to know. And these are all about how magnetic things are able to have a force. For example, this thing right here, where'd my pen go? This guy right here, there is a force, a magnetic force, causing this particle to like deflect upwards. We're going to try to now calculate how much force there is. Okay, the math's the easy part. There's two formulas. One formula works like this. This is an I, an L, and a B. I, L, B. I'm sorry it's so blurry. I stands for current. The more current you have, the more magnetism you'd have. Think back to my little thing right there. If I wanted to make a stronger magnet, I should just make more particles move, right? The more you have, the better it would be. L is length. The longer the wire, the more wire I have, the more force there would be, because there's more electrons running through it. And then B is your field. Okay. This is if you have a wire. But if you just have a particle that's moving, you use the formula QVB. Q is how much charge your particle has, V is how fast it's traveling, and B is your field strength. I'll sit here. Let's give one a try. You guys, this is going to be way easier than what we started with, I promise. Hypothetically, let's say that we have a field. So I'm going to use like a bar magnet. I'm going to try to draw this out. Here's a bar magnet. And I'm going to draw a wire. Let's make this north, let's make this south. I'm going to draw a wire that's kind of running like, I'll use an X here to imply that it's like going out of the page. And it's like it's running through there. Can you guys kind of picture what I'm going for here? Okay, so this is actually going into the page, this wire. Okay, like a horseshoe magnet. What I want to figure out is which way and with how much force is this wire going to move. Okay, there's only two possibilities. The wire is either going to move this way or move this way. So first thing we should do is figure out which way we want the electrons to flow. So why don't I make the electrons go this way? I'll make the electrons run through the wire like this. Let's say that's the way that they're running. Which means if you're hooking it up to a battery, This is the negative end of the battery. This is your anode. And this is the positive end of your battery, your cathode. Use your left hand. Which way does my hand point? This way or this way? Yeah, this kind of sucks. Okay, I gotta tilt my hand like this because it points towards the south pole. Okay, so that's step one. Then my thumb is the direction the electrons are going. So the electrons are going into the board. Which way is this wire gonna move? Towards me. That's what we'd expect to see. And when I set this up on Monday, you'll hopefully be able to see that. But this wire is going to move this way with a certain amount of magnetic force. So point down towards south, finger into page, palm is which way it moves. That's the theory part of it. Now for the math part. The math part's actually really easy. The formula for a magnetic force is I times L times B. So if you're wondering with how much force this wire is going to torque or bend, all we've got to do is take the, actually no, we're looking for current, aren't we? So this number here is 1.884. Current is what we don't know. Length is 3.45. And B is 1.29. You guys see how those numbers were all sitting there? So we just have to divide these out. I'll go to the back again, I think. So how much current would it take to make this length of wire in this magnetic field have that much force towards the right? 1.884 divided by 3.45 and 1.29. I got 0.42. I guess 3 sig digs, 0.423. So the formula we used was the magnetic force is the current times the length of the wire times the magnetic field. Okay. Now there's a couple of notes we need to make here. This wire, we only count the length of the wire that is inside the field. So even though the wire may run from here to here, the magnet may only be going from here to here. So when we do this in a lab setting, you can only count the length of the wire that is like inside of the magnet. You know what I'm saying there? Like that wire that I have right there, if I were to put the magnet around it, it would only be the width of the magnet you can actually count the length for. Oh, current is amps. A for amps. Good question. Thank you. So, and the theory behind it is that this would pull the wire that way because a magnetic field was inducing motion, basically. Okay. Set aside the theory for a bit here and the direction. If I give you 3 out of 4 variables, you guys okay being able to like plug it into a formula? I'll solve for the other one. Okay, so let's try some more of the math questions, and the theory will come. Okay, with practice. Yeah, so the unit for current is an A, amps. Let's try another one. Suppose that a positive 2.6 Coulomb charge flows through a wire of length 3.6 meters in 6.25 seconds coming out of the page. So just to like set up a picture here, let's do the same thing. I'm going to draw like a bar magnet. Why don't I make this be north and south again? And this time the wire is like coming towards us. Can I see how I'm doing that here? Now the wire is coming towards us out of the page. Can you visualize that? Maybe I'll even try to draw it in 3 dimensions here. I'm not the world's greatest artist, but maybe I'll add like a little bit of thickness to this here. How's that? Does that kind of makes sense for the bar magnet, and the wire is coming through it. Okay. We want to figure out the direction and the strength of the magnetic field. So it says that the wire is deflected with a force of 2.35 newtons upwards, which means I'm going to have to actually take this thing and rotate it a little bit, because as I've drawn it, the wire can either go this way or that way. So I'm going to need to, sadly, change my drawing. And the horseshoe magnet's going to have to look something more like this. It's going to have to go like this way. Makes sense. That's my horseshoe magnet. And the wire is still coming towards us, though. So the wire is coming that way. So this is the direction that things are traveling. Okay. Only it's not a wire. It's actually a charge. It's positive 2.6 coulombs. So this is a positive charge. When I use my hand then, figure out it with your right hand. Okay. Now here's the possibilities. Either the wire is going to go up or it's going to go down. Those are the two ways this would travel now. And I've told you that it's going up. Did you still have a question there? Because it's not going to move, it doesn't move towards the north or the south pole. It moves either out or in. That makes sense. So like in your diagram here, this would have caused it to move towards north or towards south. It doesn't move towards either of the poles. It moves in the other direction. So like if your field is pointing this way right here and it comes out of the page, it's got to go one of those two directions. That'll work, yeah, right? So because what you really have is six, you can either have up, down, side, side, in, out, right? And so if the field is already going, let's draw that. That's a good question. If the field is going side to side and the direction of travel is in, out, the only other possibilities are up or down. And I told you this one right here. Actually, it said it was getting deflected upwards. So I wonder whether I can undo a few of these steps here.
X and Y direction, it has to be
for the last one, yeah. You're going to be given an X, you're going to be given a Y, and it's one of the two Z directions. So there's only two choices that are left. You just got to figure out whether it's up or down, in or out, left or right. So what we know right here, let me try this one more time here and then ask a question. What we know is that the force is going to go up, and we know that the particles are moving this way right here. We should now be able to figure out this field. So let me go stand at the board and then ask your question if I don't answer it, okay? So we're using a positive particle, right? I'm going to use my right hand, okay? The positive particle is coming out, so I know I have to point my thumb towards you guys because the particle is coming out of the page. Okay, that's one dimension. For the second dimension, I know it's going up, but that's the force that's going up. So my palm is going up. Okay, so one dimension was out of the page. Then there was the palm direction going up and down. Which way is my field going? That way. So which side is which then? This side right here would be north, and this side here would be south, because which way do we define a field? Always going towards the south, because that's what a compass would do. So based on this information, out of the page means towards you. Palm is the direction of your force. This is now north and south. I now know the direction of the magnetic field. If that didn't make sense, don't stress, okay? We've got time. This sucks. This is like my least favorite lesson in all of Physics 30. Yeah. They'll have to, yeah. They'll have to give you X and Y, and then you solve for Z, or Z and X and you solve for Y. They'll have to give you two of the three somehow. So if that makes sense, this was now the north pole of our magnet, and this was the south pole of our magnet. Okay. That's probably the hardest part. Most kids really struggle with like the orientation part. Let's do the math, because the math part for this is way easier. Okay. We have two formulas. I have the formula of Fm equals ILB. That one doesn't really fit here. Why don't we use the other formula, which is QVB? Now, I have a force, right? This force number here is 235. I have a charge, 2.6 coulombs. I don't actually have a velocity exactly, but like we can make a velocity, can't we? What's velocity equal to? Distance over time. So even though I don't have a velocity, I can just make it my distance divided by my time. And there, now I can solve for how much field my magnet must be providing. So don't forget, a field is based on how strong the magnet is. The force is what the magnet is able to do to something. Can I say that one more time? The field is like how strong the magnet comes as. But the amount of force it can provide depends on a few factors. It depended on the speed and the charge of the particle. So now you just have to rearrange this for B. So 2.35 times 6.25 divided by 3.6 divided by 2.6. My calculator spit out this as an answer. Let me know if you don't get this. 1.5, nope, 1.6, I guess, if you round it. You guys get 1.6? What unit is a magnetic field? Do you guys recall from yesterday? T for Tesla. Yeah. So that's how strong this magnet is, 1.6 Teslas.
Why is IQ?
It's ILB
Oh, it's this one.
and QVB.
Oh, okay. That's for the particle.
Yeah. And I like the way you've written that, wire and particle. That's good. Okay. I'm sorry, guys. Like I said, this is my least favorite lesson. Like, this is not a fun one. So, okay, let's try another one here. Let's say an alpha particle moves through a Tesla field. How much force will it experience? Let's not even worry about directions right now. Let's just focus on the math here. You have an alpha particle. That indicates you should use the formula QVB. Yeah, so if we were to use our hand, use your right hand. We're just not going to bother with direction anymore because like you're probably sick of the whole direction thing anyways. You're probably like, I don't even get it. Or maybe you do, but let's just do the math part. How much charge, though, does an alpha particle have? Yeah, it's 2 of these. Good. I think you both kind of had the same thing. You just Malik said it faster. So 2 elementary charges times by your speed times by your Tesla force. Okay. So the examples I've got here are not overly challenging, which is good. And I think they did that on purpose. They made the math for the magnetic stuff quite simple because the theory behind it sucks. Okay. And you're always manipulating your hand around and you're trying to figure out which way that stupid thing is wrapped. And I got to be honest, I've been doing this for 12 years and I still sometimes struggle as to like which orientation to use. So do not feel bad if like it takes you a while to get this. I really hope though that Monday when I give you guys a chance to like play around and try this, that'll help. Okay, so it was an alpha particle. And so an alpha particle has 2 elementary charges to it. Do you remember what an alpha particle is? The alpha particle is with this symbol here. It's 4 and 2. It's basically a helium nucleus with a +2 charge to it. So, okay, let's do the math here. 2 times 1.6 e minus 19. And then times by 1.22 e4. Kind of like Philip pointed out, though, if we were to do a hand rule, though, we would have used our right hand. I got, I guess with rounding, 9.0 e minus 14. Anybody else get that? Okay, and then this is a force, so newtons. Yeah. Well, keep in mind, this was just a single alpha particle moving, right? So think about this. He said it was really small, right? A single electron flowing through a wire wouldn't really have a whole lot of force acting on it. But what if you had a whole bunch of electrons? Then you'd notice it, right? So a single particle won't have a whole lot of force on it, though. Okay, the one thing I need to now do is show you guys how to combine formulas more, okay? On their own, most of these formulas are pretty straightforward. But one of the things we have to be able to do is combine forces. For example, if you guys haven't already researched the Millikan oil drop experiment, the basic way that that worked is that gravity wanted to pull drops of oil down, but Millikan set it up so that an electrostatic force kept these little droplets hovering. And he basically made Fe equal to Fg. It is very likely that you're going to be asked questions where you have to make forces equal each other. Now, there's 4 main forces you guys have to be able to work with. Here's the 4. You have to be able to work with gravity, electrostatics, and magnetics. And sometimes we throw in centripetal force, if you guys recall that from last year. These are the 4 forces that at some point you're probably going to make them equivalent to each other in some sort of like scenario. Okay. So let me provide a scenario for you here. Imagine there's an electron, and the electron is about to move into a field. Which way is this field going, by the way? Into the page. Okay. So it's like there's a magnet behind us, and there's a magnet in front of us. Okay. The magnet behind us is a north magnet, and the magnet in front of us is a south magnet. If you can kind of picture that, right? That's why this section sucks. It's so like abstract, and it's so like you have to have a good spatial awareness. It's going into the page, it's going south. Well, basically what I'm going to say is the field is going into the page here, and I'm going to use my left hand. Why am I using my left hand? Because it's an electron. Which way is it going to be deflected? This way. So if that's what you meant by south, then sure. I thought down would have been a better word to use, but yeah. So there's a south pole in front of you. There's a north pole behind you. The electron's going this way. Which way will the electron start to like bend? It'll start bending according to your palm, which is down. Should I go like up to the board here? Okay, let's go to the board here again. Okay, so over there, south magnet. Janae's room, no, behind us, north magnet. Janae's room's got a south magnet. We're gonna point our hand into the page. Okay, now we can rotate it like this if we want, but does everyone agree that our hand's pointing into the page? The electron is going this way, so my thumb goes that way. So that this is one dimension. This is the second dimension. The electron then is going to start going like this. Okay. Now, if the field is big enough, it's actually going to start going in circles. Because as it starts moving, it's going to start actually making like a centripetal rotational motion. That's what we're going to try to figure out is how much of a radius is this thing going to have as it deflects. Here's how we solve this. Okay. Hopefully you guys will agree with me that we have a magnetic force. Okay. That magnetic force is going to be equal to a centripetal force causing this thing to start going in kind of a circle. So let's start putting some formulas together. What's the formula for a magnetic force for a particle? Q, V, B. Okay, I didn't teach you this, but you guys remember the formula for a centripetal force? Okay, it is on your formula sheet. It's either MA, or probably like this works best, MV squared over R. Does that ring a bell? If you need me to, I can do like a rehash of a lesson of Physics 20, but if it's okay, like this is the formula for centripetal force. What we need to now do is merge these two formulas together and isolate for the radius. So if you guys can kind of picture how I'm going to pull this off, the radius will be equal to mv squared divided by qvb. I've now managed to make my own formula. And this is the part that most kids don't like about Physics 30, is like one formula by itself, sure, I can math that, right? But we've got to figure out how to merge formulas together. At this point, it's actually pretty easy. What is the mass? Well, it's an electron. The mass of the electron is on your formula sheet. It is 9.11 times 10 to the minus 31. That's 911 10 to the minus 31. Okay. Do we know the velocity? Yeah, it gave us that. That was 2.38 10 to the 5. Do we know the field strength? Yeah, it's 1.13 E5. I feel like you guys are a little ahead of me here. What can I do with these velocities here? You can, yeah. So we can actually get rid of one of these velocities here, and rather than square it, we'll just use 1. And then finally, what is the charge of a single electron? 1.6 to the minus 19. And that's how we start to figure out how this guy starts going in circles. Now, some people may ask, Chris, why is it going in a circle? Why doesn't it just go down and keep going down? Can I explain that real quick here? So keep in mind, I'm going to the front here, right? My fingers are always pointing into the page, right? Okay. If you agree that my thumb is going this way, there needs to be some force going down, right? But what happens once it starts going this way? Well, now which way is my palm facing? Well, now it's going this way. And then as soon as it's down, now which way is my palm going? Does that make sense? And so like as it rotates, the force continues to go center seeking. That's where the word centripetal came from. The force will always be trying to go to the center. And like I can't keep doing that obviously, right? But like it's gonna keep going around in circles. So anyways, do the math on this. And let's calculate what its radius would be. I got 1.18, negative 11. Let me try mine again. It's 9.11, by the way, 911. 2.35. Oh, no, I made a mistake too. Never mind. I'm wrong. I see my mistake. Okay, how about 1.20? 1.20 to the minus 11? Hey, you have that. Perfect. Okay. So I calculated this. Sorry that I'm a little messy here. Your radius, I got 1.20 e to the minus 11. And the unit for that, being a radius, would have to be meters. So that would be the turning radius as this thing starts to go in circles. Any questions? Maybe I should phrase that differently. I don't expect that you fully get it, but do you have any questions that you can think of at the time? Because you may just want some time to process and to think later, because this is a weird lesson. Okay, let's try one last one. We'll call it a day. You have an alpha particle moving towards that same field. Here's what I want to do. I want to figure out the velocity needed so that the force of gravity balances out the magnetic force. Here's what I want to have happen. This particle right here would normally want to deflect. Normally it would want to go in circles. We want it to go in a straight line. So we don't want it to deflect. Here's what that means. We need the force of gravity to be equal to our magnetic force. Guys. Okay. So that whatever pushes it up, it gets pulled down the same way. Let's talk about why that works. Okay. I'm going to do the exact same thing, only know how it's now an alpha particle. Okay. I have to use my right hand now. My right hand is going into the page, and it's flipped like this. Which way would this particle want to go? It would want to start deflecting up. But gravity is going to pull it down. So I want to make it so that whatever it wants to deflect up, gravity keeps it going in a straight line. So that's where I came up with gravity equals magnetic force. Ugh, sitting back here is not working well today. So let's make our own formula. What's gravity equal to? Mass times gravity. And your magnetic force, QVB works. What are we solving for? We need to determine the velocity needed. If this thing goes fast enough, it won't actually, gravity won't affect it, is what I'm basically saying. So to solve for V, we'd have to do mg divided by QB. You guys kind of picture how I did that? Divide both sides by that. But we have all the information we need. What's the mass of an alpha particle? It's on your sheet. You just got to find it. Mass of an alpha particle, stealing off a Will sheet, is 6.65 e minus 27. That's the mass of an alpha particle. As long as we're on Earth, the gravity is 981. The charge of an alpha particle, 2. 1.6 times 10 to the minus 11s, or 19s, sorry. And the magnetic field is still the 1.13 times 10 to the 5. I got 1.8 to the minus 12. But I got to check that again. How many sig digs would that be? I need 2. I got 1.80 to the minus 12. You did too. You did too. Okay. These guys did as well. That was a velocity. That'll be in meters per second. So here's to recap what's happening. Normally, as this particle goes through the field, it would want to deflect upwards. Normally it would want to. But gravity is going to try to pull it downwards. If I make these two forces equivalent to each other, it would then, in theory, go in a straight line. Okay, one last thought, and then we're going to call it quits for a day. Thank you for staying with me, guys. This lesson sucks. It is my least favorite one I have to teach. Okay. What we're going to talk about next day is some practical applications, including how a motor works. I brought the motor out to the front, but I actually discovered this one doesn't work because the little pieces on it are kind of corroded. So this is meant to be like a next time in Physics 30, here's what we're going to learn. We're going to talk about some of the applications behind these. Okay. So I'm done here. So let's do a quick recap of what we talked about. We learned about we're doing him next. We learned about Ørsted and his discovery that magnetics and electricity kind of relate to each other. Okay. Just so you guys know, they will, on the diploma exam, possibly test you about some scientists and their contributions. So don't ignore them. I would not say memorize like the years they did things in, but like they will ask you like, who did this? So know that Ørsted was the first guy who came up with magnets and electricity. We learned 3 rules for hand rules. They're annoying. I don't expect you to fully get it until after our activity on Monday. Okay. When I can give you some stuff and you can kind of try it yourself, I think it'll make more sense. So if you do feel like you have it, because a few of you are like correcting my mistakes already, that's awesome, but like don't stress if you don't get that yet. The most important thing today though is I introduced 2 new formulas. Can you use the new formulas? Okay. If you can use the formulas, then today's a success, and eventually we'll figure out these hand rules. Okay. Oh wait, last thought, then you guys can go. I have something on the board I talked about with my 9s and my 10s this morning. I wanted to give you guys the same spiel, but we're starting to figure this out, I think. Here, sorry, let me go first. One of the things I'm really trying to encourage in my students is get me to give you feedback. And I feel like we're finally getting to the spot where like I should be crazy busy all the time because I'm always talking to somebody. Like you should hopefully be like waiting in line to try to talk to me. That's what I want. Not because I want to be like popular, but I want to have a conversation with you guys because I think that helps you learn better. So here's the thought I had. You guys can have me check over stuff before you hand it in if you want. I will pre-mark it for you, give you some sticky notes and say, here's how you can do better. Okay. If you don't do well, you can resubmit it after it's marked and like do it again. I'm fine with that. Okay. And then last, if you still don't have the mark you want, I will still give you more assessments. Okay. One thing that I've kind of realized is that I went into this year kind of assuming that you guys knew that that's how this was going to work. So I need to apologize. I didn't communicate that well enough. Okay, I just kind of figured that that's how things worked in the school. But like, if you need to do anything to improve your marks, those are kind of your options. Okay, so have me mark it before you even hand it in, redo it, and like honestly, you can almost redo anything. The only thing you really can't redo, I think, is a quiz or a test, because you know the answers. But like, I can make you another quiz or a test if you really need one. Okay, what I really am hoping for is that everybody has 100% on all of their labs and assignments. Okay? Because if you don't have 100%, I'll just send it back to you until it is perfect. Okay? Unless you don't care. If you're happy with 98 or 82, then fine. I'm not going to make you. Okay? And then, yeah, the last one here. If you guys need better marks, I will let you have better marks. All I care about is that you learn. Okay? So with that being said, I need you guys to start moving forward. If you're still doing momentum stuff, you got to stop. Because we got to practice this new stuff. So can you guys start working on assignment 2? Can you start finishing up the activity we did last week? Can we go over your quiz if you didn't do well on your quiz? Next week is going to be pretty busy. We're going to do an activity on Monday where you guys play around with magnets. And on Wednesday, we're going to do a lab where we actually do some calculations of forces and fields and stuff. Okay. So next week's kind of a busy week. I'm going to put 2 new things on your plate. So between now and then, can you guys try to wrap things up otherwise? Sound good? So tomorrow's a work day, by the way. I have nothing planned for tomorrow other than just time. So, okay, I think I'm out of time and I'm out of breath. Come ask me questions if you need. Thank you, everybody.